So let's take a look at how we're going to test out our alternative hypotheses. So the way we're going to do this is we're going to use what's called a test statistic. So the test statistic compares our observed outcome with the outcome we would expect to get if the null hypothesis was true. And this is I think, a difficult concept. So really pause and think about what we're saying. It's going to take our observed outcome. What I mean by observed outcome is whatever we got in our sample. When I flipped the coin, I observed that it landed on tails 20 out of 20 flips. That's the observed outcome. We want to compare that to what we would expect to get if the null hypothesis were true. If it was a fair coin, for example, or if the population proportion in that previous example, if the population proportion were still at 55%. That's what would happen if the null hypothesis were true. We compare what we observe in our sample to what we'd expect to happen if the null hypothesis were true. When the test statistic that we calculate for this observation here, the test statistic is far away from the p-naught value that we would expect to get if the null hypothesis were true, in that case, then we reject the null hypothesis. And in that case, we conclude that the evidence supports the alternative hypothesis. So if we get an unusual test statistic, a test statistic that is far away from our expected value, then we reject the null hypothesis and we have evidence to support the alternative. How do we get the test statistic? So we can calculate it by hand, and it's really very similar. It is really the same idea as what we used to calculate a z-score earlier in the course. So our test statistic z, we can calculate it by taking in words, it's our observed value minus our null value, so the p-naught value that we expected, divided by our standard error. In symbols, we can say this is p hat minus p naught divided by the standard error. So p hat is the sample proportion. P naught is the proportion we used for the null hypothesis. How do we calculate the standard error? That would be the square root of p naught times 1 minus p naught divided by n. And I hope you notice both of these have the same structures they've had previously in the course. In Chapter 7, we used a little bit with z-scores. And I know we use the standard error formula, and it's the same formula except instead of p, we don't know what p is, so we're using p naught. The z-score formula, earlier in the course when we calculated z-scores, you may remember way back when, z was equal to x minus the mean divided by sigma, the standard deviation. This follows that same pattern. P hat is our sample statistic that we observe. P naught is the mean value proportion we expected. And standard error, remember, is the standard deviation for our sampling distribution. So it's the same structure we've always used. So part E says, calculate the test statistic for the global warming example. So this was from the previous video. So let's go back and look at what we said in the previous video. We said that p hat was 0.68, n was 1,000. We said that the null hypothesis was that p was equal to 0.55. And the alternative was that p was greater than 0.55. So to calculate our test statistic that goes with this, let's see what we need. First, we need our standard error. So let's go ahead and compute the standard error. So it's going to be the square root of p naught. So p naught, remember, was this number right here, our null hypothesis proportion. So 0.55 times 1 minus 0.55 divided by n, which was 1,000. Remember, our sample size was 1,000. Okay, and then let's compute that. I'm getting 0.01573 from my notes, so I think that's our standard error. Our z-score is going to be p hat minus p naught divided by the standard error. So p hat is your sample proportion. P hat is what you obtain in your sample. So in my sample, I took a survey in 2017 and I got a value of 68% for my survey, my sample and my survey. So p hat is 0.68 minus p naught, which was my null hypothesis proportion, which is 0.55, divided by the standard error that I just computed, 0.01573. And I'm getting a z-score of about 8.2. 8.26. That's my test statistic, 8.26. First of all, I want you to recognize why it's positive. It's positive because the 68% was to the right of the expected 55%. Ultimately, what we're going to say is this still follows a normal distribution. So if you think about your normal distribution, remember the central limit theorem says, I expect the 55% to be right in the middle. My 0.68 is above that. So my z-score should be positive, okay? Now, how unusual is that test statistic? How unusual would it be to get a sample of 68% if the null hypothesis were true? Well, that's what the test statistic tells you. Think about if I said to you something was 8 standard deviations above the mean. That would be really, really unusual. Remember, all the data just about falls within 3 standard deviations of the mean. So 8.26 is highly, highly, highly unusual. And in this case, it would be highly unlikely to get a sample with a test statistic of 8.26 if the null hypothesis were true. So let's kind of write some of this out. So let's summarize what this means. Let's interpret this. I'm really short on room here on the bottom. So let me make some space right above it. I think you've got more room on your paper. So remember that our test statistic was 8.26. So what does this indicate? So while the null hypothesis claimed a population proportion of 55%, the observed sample proportion of 68% is much higher. Much higher. How much higher is it? It is 8.26 standard errors above the expected 55%. Okay? So hopefully you're thinking, well, that's really, really, really unusual, right? It's really unlikely that I would get a population with a that I would get a sample with a z-score of 8.26 if the population were still at 55%. And so this would lead us to reject the null hypothesis. So let's get into that a little bit more here. How do we know when to reject the null hypothesis? So the p-value is a probability. First and foremost, when you hear us talk about p-value, that is a probability. The null hypothesis tells us what to expect when we look at our data. So in that last example, I expected to see 55%. If we see something unexpected, that is, when we are surprised, then we should doubt the null hypothesis. If we are really surprised, then we should reject the null hypothesis. So we would reject the null hypothesis altogether. That last example, we were really surprised because we got a test statistic that was 8 standard errors above the expected value. That's really, 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 really unusual. The p-value gives us a way to numerically measure our surprise. It reports the probability that if the null hypothesis were true, our test statistic will have a value as extreme or more extreme than the value we actually observe. So small p-values that are close to 0, in other words, small probabilities that are close to 0, mean we are really surprised. Okay, so if we get a small p-value, and we'll get this p-value from StatCrunch. We're going to use StatCrunch to help us calculate the probability. But if we get a small probability, that means we are really, really surprised to see that sample if the null hypothesis is true, which will lead us to reject the null hypothesis. Larger p-values that are closer to 1 mean that we are not surprised. We are not all that surprised. It's expected, not that big of a deal. How do we decide what's our cutoff for values that are surprising? That would be our significance level. So the significance level is the probability of making a mistake, of rejecting the null hypothesis when in fact the null hypothesis is true. And, there's a lot of theory behind this, and we're not going to get too involved in making mistakes and things like that. But I do want you to just know what we're going to use the alpha for, the significance level. The symbol for it is alpha. So for our purposes, we're going to use a significance level of 5%. Sometimes we'll use 1%, sometimes we'll use 10%. It depends on the application. In most social sciences, we use 5% as our cutoff. But what I say cutoff when I say 5% is to compare this to our p-value. So if our p-value is less than 5%, for example, that's a really small p-value, and that means we are really surprised. P-values over 5% means we are not so surprised. Okay, so here's where it kind of comes together. P-values and the significance level. If we get a p-value that is less than or equal to our significance level alpha, whatever that is for the particular problem, our p-value is considered small. We are really surprised, and in that case, we reject the null hypothesis. On the other hand, if we get a p-value that is greater than our significance level, our p-value is not considered small, we are not surprised, and in that case, we do not reject the null hypothesis. So let's go back to our global warming example here, and let's think about what our p-value would be. So it says label the x-axis under the standard normal distribution below, given with the appropriate z-scores. Okay, so just a regular standard normal distribution. Remember, 0 goes in the middle. This would be 1 standard deviation. This would be 2. This would be 3. And of course, -1, -2, -3. All right, so this is a standard normal distribution. Recall that the test statistic calculated for the global warming example was 8.26. Where would this test statistic lie on the above axis? So if we were to extend this out really far, 8.26 would be out here somewhere. Okay? I can't even draw how far out it would go, so I'm just going to stop there. So our 8.26 is way out in the extremes. Based on the graph and what you know about z-scores, what do you think the probability of getting a test statistic at least as extreme? So that means here or more extreme. At least as extreme means we'd shade this way. This would be more extreme than the 8.26 as the one we calculated. This represents the area in the right tail. So, you know, don't think too much about this. Anything past 8 standard errors would be so unlikely, right? So another way of asking this is, what is the probability of getting a z-score above 8.26? What is that probability? And so we would say very small, almost impossible. It's almost impossible. I mean, in practical terms, in the real world, it's impossible to get a test statistic that extreme. And so that means we would have a very small p-value. The p-value, remember, is probability. So the p-value is the area that you shade in here. Your p-value is this area that you shade in here. So in this case, that p-value would basically be 0. Okay? So it says use the normal calculator on StatCrunch to find the p-value. I'm not going to use the calculator to do this because we know it's so small, it's such an unusual, unlikely possibility. The p-value, we're just going to say it's 0. So does this p-value give us evidence to reject the null hypothesis? Well, when do we reject the null hypothesis? Go back to this chart back here. We reject the null hypothesis when our p-value is small, when our p-value is less than our significance level. Now, I didn't give you a significance level in this example. However, the p-value is 0. Is that a small number? Yes, it can't get any smaller. It's a probability. It can't be negative. So yes, we're definitely going to reject, since the p-value equals 0 is very small. It really can't get any smaller. So we are definitely going to reject the null hypothesis. So what can we conclude about the percentage of Americans who believe that global warming is caused by human activities? Has that increased from the 2015 to the 2017 year? So we would say yes, since we rejected H naught. Why did I reject H naught? Based on that p-value that I calculated for my statistic of 8.26. We rejected H naught. So we can say there is evidence to support the alternative evidence, or the alternative hypothesis. And the alternative hypothesis was that the percent Here, I'm going to come down here and write this, and I'll erase it. Percent who believe global warming, or climate change, I guess was the term they used. Climate change has increased, and what has it increased from is increased from the 55% that we had in the 2015 year. And so we compare everything to what P0 was, what it was in the first year, which was 55%. All right, let's do one last quick example here. So it says, according to census.gov, Duval County is about 30% African American. Suppose you are looking at jury pools for Duval County. Each jury pool has 400 members in it. The null hypothesis is that the probability of an African American being selected into the jury pool is 30%. And so that's coming from the population for Duval County, which is 30%. So the question says, how many African Americans would you expect on the jury pool of 400 people if the null hypothesis was true? Okay? So if the null hypothesis were still true, what would we expect? Our expectation for our jury pool of 400 people. So the null hypothesis would be that P equals, let's write this out, H naught is that P equals 0.30. So our expected number of people on the jury would be 30% of 400. So 0.30 times 400. So we would expect to see about 120 African Americans on the jury pool, okay? Could it be more? Could it be less? Absolutely. It's going to fluctuate from one jury pool to the next, but we expect it to match the population of the county, the proportion of 30%, so we expect about 120. Suppose we get a pool A contains 100 African Americans out of 400, and pool B contains 130. Which will have a smaller p-value and why? So let's write a few things down here. Pool A had 100, and pool B had 130. So we can think of this as normally distributed, and if we think about it visually, in the middle, there's a couple of things we could put. We could put 30% if we want to, 0.30. We could also just put the numbers. So the numbers that we expect 120 based on part A here. Pool B is down here at 100 and pool A is at 100 and pool B is over here at 130, okay? So which one is closer to the expected value of 120? The one that's closer distance-wise, I hope you see, the one that's closer is the 130 because there's only 10 apart versus the 100 where there's 20 apart. So let's jot that down. So pool B is closer to the expected number of 120, okay? So the question says which would have a smaller p-value. Well, p-values go out to the extremes. So which one is more extreme is another way of thinking about that. So since the 100 pool A is farther away from the mean, that will have a smaller likelihood. So let's write that down. So since pool A is farther away from pool B, I'm sorry, not pool B, sorry, from the mean, that's what you want to say, from the expected value, let's do that. The expected 120, there's a smaller likelihood, smaller chance, let's say, for pool A, and that indicates a smaller p-value. So I really encourage you on a question like this, and actually on a lot of these questions, make a quick sketch and shade in when you need to shade in, and think about what's going to happen. This p-value, what we're talking about, would be here for pool A, so something as extreme or more extreme, whereas for pool B, it would be over here. So the area contained in the extremities for pool A is going to be smaller than the area contained for pool B.